Hello. So today I want to talk a bit about a different type of energy, and that's the type of energy that's stored in springs. Up to this point, you've done examples of potential and kinetic energy just based on gravity. And in that case, the mass always cancels. Well, this is one example where the energy stored in a spring has nothing to do with the mass that's pushing on it, so mass becomes relevant again. The idea behind Hooke's law is that when you have a spring, it just has a natural rest position. I can pull the string and stretch it, or I can push the string in and compress it. And if I do that to a spring, then it basically takes up a different distance. It's kind of a way of thinking about it. It has a different length. That change in length from its rest position, we will define as x. So whatever amount by which it's longer or whatever amount by which it is shorter than it usually is if nothing is tugging on it or pushing on it, we will define as x. So that brings us back to Hooke's law, which tells me that the force that a spring exerts when it's being compressed or stretched is negative kx. K is this new idea called a spring constant. Each and every spring has its own spring constant, and it's just the property of the spring. It's in units of newtons per meter, which tells me if I wanted to stretch a spring a certain, let's say 1 meter, it tells me how many newtons I would need to do it. The more you stretch it or the more you compress it, the more force is required. And if you've ever experienced I keep saying strings. If you ever have experienced springs in your life, then you probably know the farther away you try to stretch it, the harder and harder it becomes to stretch it anymore. Same deal with compressing it and squeezing it in. So a lot of springs have spring constants that are pretty big, and that's just because 1 meter is a really long distance to stretch it. So you would need a whole hunkin' lot of force to do that. Not only can I figure out the force, oh, and by the way, this negative where it says it equals negative kx, where k is the spring constant and x is the distance away from its rest position, the negative just tells me it's in the opposite direction. So if I pull a spring to the right, I feel a force from the spring to the left. So that's all that the negative is. Not only that, it stores up some potential energy. If I set an object on a spring and push and compress that spring down, it gets spring-loaded. If I then let it go, that compressed energy inside the spring converts over to kinetic energy. So that compressed energy within the spring is what's known as elastic potential energy. So I often call that UEL or U elastic or something like that. And it equals 1/2 times k times x squared. 1/2 times the spring constant times the distance it's compressed or stretched away from its rest position squared. And that's going to be in units of joules, just like every other bit of energy. One last bit I want to talk about before we go away from this energy section is about power. Power and energy are very closely related. The way I like to introduce this is by talking about a sports car. If I walk up to you and I'm like, yeah, I got this rad new car. It can go from 0 to 60. Okay, cool. What's really impressive, though, is how fast you can do it. I can go from 0 to 60 in half a second. Whoa, probably not. But that's what power is. So power is just the work that can be done divided by the amount of time it takes to do it, or the change in an object's energy divided by the time that energy was changing. So the units will just be joules per second, since work and energy are both in joules and it's divided by time. And a joule per second is a watt of power. So we'll do some more examples of this. Essentially, people have useful power outputs, and I can figure out, if I know my power output, how long it'll take me to do a certain task, or something like that. In fact, speaking of the power of people, we hope you'll join us in class, probably next week, where we ask the question, are you as powerful as a horse? So I very much look forward to that. But before that, I want to talk about just one more thing very quickly, and then I'll end this video, and that thing is momentum, and more specifically, how we can use momentum to learn about collisions and the conservation of momentum within collisions. So first and foremost, momentum is just an object's mass times its velocity. Think about it this way. If I chuck a ping pong ball at you at 40 miles per hour, that is going to hurt, but you'll be fine. If I chuck a piano at you at 40 miles per hour, that could be a different story, because the piano has a good deal more momentum that it would transfer to you upon the collision. Yikes. Linear momentum is often denoted as lowercase p, because m is already taken by mass and meter and everything else. So momentum is p, it equals mass times velocity. It is a vector, so once again, x and y components will come into play here. I can have momentum in a certain direction versus another. The units of this thing, well, if we do a little bit of dimensional analysis, plugging in for mass, I get kilogram. Plugging in for velocity, I get meters per second. So all in all, I end up with a kilogram meter per second. And that's it. That's the unit of momentum. It didn't get its own special name. Sad day for momentum. It does, however, get its own conservation law. Within the conservation of momentum, it essentially says this: within an isolated system, so that basically can consist of as many objects as you want it to, but make sure you've got a clearly defined system of 2 objects, 3 objects, 17 billion objects. The total momentum will be conserved as long as there's no force coming in from outside the system and messing with things. So that means even if the objects within the system are colliding with one another, the momentum before the collision and the momentum after the collision will always be the same. Now there are a couple of different types of collisions. We've got elastic and we've got inelastic. With elastic collisions, the objects kind of bounce off one another. Think of an elastic bouncy ball. It bounces all over the place. Similar to elastic collisions, where the objects strike each other and then bounce off in different directions. When that happens, between the 2 objects, the momentum and the kinetic energy are both conserved. So here's what I mean by that. Let's say I've got, let's be crazy creative with it, and I've got a ball, and it hits another ball. I'll call one ball A, ball B, and they collide. I can find initially, before the collision, the momentum of ball A and the momentum of ball B. Through the entire system, I'll just add the momentums together to get the total momentum of this 2-ball system. And I'll go ahead and put a little I here to indicate initial before the collision. After they collide, then A and B will probably bounce off in different directions. And I can find the momentum of each one individually, so PA final plus PB final. And the sum of their momentum before and after the collision will be the same. So that means mass of ball A times velocity of ball A plus mass of ball B plus velocity of ball B is exactly the same before and after the collision. Not only that, but with elastic collisions, the total kinetic energy of the system is conserved. That means 1/2 times the mass of ball A times the velocity of ball A squared plus 1/2 times the mass of ball B times the velocity of ball B squared is also going to be the same before and after the collision, with elastic only. There's another type called inelastic collisions. That's where some of the kinetic energy is lost, and usually it's lost to heat. This is kind of more realistic. There are very few perfectly elastic collisions that you're going to find necessarily in standard Newtonian physics. But momentum is still conserved, and that's how momentum is a really, really useful thing when you're studying what's going on with these collisions. Now there's another condition called perfectly inelastic. If it's perfectly inelastic, there is no bounce at all. The objects just stick together. As much kinetic energy as is possible is lost in the collision, but get this, the momentum is still the same before and after. And if the two objects stick together, then their final velocities after the collision have to be exactly the same. They've got to be, because they're stuck together. So that makes these momentum problems actually a little bit easier. Before the collision, I've got mass of ball A times velocity of ball A plus mass of ball V times velocity of ball V. Afterwards, I would have ma times this single velocity together. They're both traveling at the same velocity, plus mb times that velocity. And I can actually factor the velocity out. And my final condition would just be v final times the sum of the masses, since now it's just traveling together as one hunk of mass for these inelastic collisions. Some examples where you might see that, as a safety feature, cars' bumpers are designed to crumble when they experience an impact. And if cars hit each other perfectly, the car's bumpers might crumble and stick together. Maybe. Generally, it's not perfectly inelastic, but that's just one example that we'll look at. Okay, so we'll talk a bit more about how to do these types of problems in class, and look at some examples and do some demonstrations with this. But until then, have a fantastic morning, evening, night, Bye.